Okay, everybody, let's go ahead and go through this strategy passage number 4 now. Okay, everyone just got done with it. Now it's a little bit shorter of a passage, only 4 questions were here. So remember, our typical MCAT time is about 1 minute and 40 seconds per question. So this would have been about 6 minutes and 40 seconds, about a 7-minute passage. All right, with only 4 questions. Definitely always something you want to consider in terms of, is this an hour later passage? Is what's my yield here? Okay. Now you see we got 3 paragraphs here, and we've got 2 figures and 1 table. All right. Now, kind of big picture here, right? What this is, of course, talking about what's going on with the lungs and intermolecular forces. All right. You want a kind of big picture here? This is all about your IMFs. Okay, your IMFs between these different surfactants and water. What's happening here? Now, our first, of course, paragraph, you always want to kind of get an idea of location, not necessarily understanding, but a quick summary is type 1 versus type 2 cells. And, of course, they also give you a few numbers here. That's going to be about 95% of the actual surface is going to be the type 1 cells, but the actual number of cells is more type 2 cells. Okay? So 60% of total cells is type 2, but in terms of the surface area, it's almost all type 1 cells. And they go on to tell you that, of course, that here you've got gas exchange, and here these guys are producing that surfactant. All right, that surfactant. And they also give you a pH. All right, pH is definitely something to kind of pay attention to because that is our physiological pH. That, of course, is what you're going to see in that alveolar fluid. Okay? Then we go on to our second paragraph. And, of course, we see that they talk about now surface tension, and they define it for you. So it's kind of a good idea to get a definition of like what exactly is the surface tension. That's going to be the energy required to increase the surface area. And they go on to tell you that the surface tension here is going to decrease with increasing surfactant. All right, so it's a trend you want to kind of note, right? Lower surface tension, more surfactant is present. So I'm going to note that on my scratch paper. Then they talk about in figure 1, the water with the surfactant. And of course, they kind of give you these force diagrams here of this, larger force diagram of the water molecules attracting other water molecules. But then the little white dots up there, they give you the surfactant. And if you notice, of course, the force arrows are smaller in the surfactant interacting with the water molecules, which is going to be important for our question here too later on. Okay? So water with surfactant, and then in the next paragraph, they go on to talk about 4 different artificial surfactants. Okay? Give you the long chemical names for all those. Again, I don't need to understand all that right now. I just need to know that, okay, here's my list of artificial surfactants. Because when they go on, in the actual next figure, figure 2, they talk about, of course, that we see the surface tension versus surfactant concentration. And it was mentioned in the paragraph, but also, you see it evident in that figure 2, that at a certain amount of concentration, you really have diminishing returns in terms of the reduction of the surface tension. Right? Now remember our trends here. You have surface tension, and always watch directionalities. You see that surface tension is decreasing, right? And that, of course, the concentration of the surfactant being used is increasing towards the right. Okay? So as you go down the y-axis, you see a decrease in in the surface tension. As you go from left to right in the x-axis, you see an increase in concentration. All right, so there's something to note that you do have an upper limit, kind of like enzyme kinetics. And then, of course, the last little table is the surface tension and entropy. And if you notice a quick little trend, decreasing surface tension also corresponds to a decrease in entropy. Okay? So that's our quick little passage highlighting, and the scratch paper what I kind of would have jotted down as I was going through and highlighting. Now, let's get into our questions. Okay? So let's go ahead and start with good old question number 1. Now, they ask which of the following has the greatest surface tension. Okay, which of the following has the greatest surface tension? So we go back and define, okay, what was surface tension, right? It was the energy required to increase the surface area. And they gave us some numbers, right? They gave us, of course, the number in that second paragraph for water. They gave us the number for ethanol. And then they gave you that number for that tetramer, or what they call it again, the heptane, all right, for the heptane. Okay, of course, the 7-carbon heptane. Now, they tell us, of course, that ethanol, if you remember the structure of ethanol, which is a smaller molecule, you see the number is greater than it is for heptane. So, and they also tell us it's the intermolecular forces that are going to be the biggest dictator of surface tension. Ethanol is going to, of course, have an OH group on it, right? So you're going to see that OH group gives that smaller molecule a higher surface tension. So if you look at our answer choices here, right, you see that in B, that's just simply a bunch of hydrocarbons. No alcohol, so no intermolecular force there. These are only going to be experiencing van der Waals. And you also see the same thing for answer choice D. That would only be experiencing van der Waals interactions, not these additional intermolecular force of the hydroxide group, that hydrogen bonding it's capable of. So then it gets down to us between A and C. And you notice the difference is that A is going to be longer than C, which is slightly shorter. So which can experience the most overall intermolecular forces? Even though they're the weaker London dispersion forces, we see that A, of course, that one actually has 6 carbons, whereas B only has 5 carbons and more hydrogens. So we're going to go with A, all right? Because it's going to experience more intermolecular forces and it's got the hydroxide group on it, giving those stronger intermolecular forces. Questions on number 1? All right, number 2. So of course you can think of this one as kind of like a memory because you remember about the intermolecular forces, and also somewhat explicit. It actually said that kind of trend within the actual passage. All right, talking about the intermolecular forces at play. Now number 2. All right, this is kind of what's going on with the experimental parts of the passage. So based on the passage, which of the following would be true in order for the surfactant to reduce the surface tension of water? So this goes back to, of course, figure 1 here. All right, looking at what's going on in that figure 1 with that weird little interactions. Now, Roman numeral 1, okay, they're telling us that the surfactant interactions are weaker than the surfactant-water interactions. So our surfactant to surfactant interactions, right, is less than, they tell us, the surfactant and water interactions. Less than surfactant, all right, H2O. All right, so if you think about this, okay, now we want to, of course, when we do Roman numeral type questions or strategies, we want to go ahead and find one that's in both answer choices. Now, 1's in 3 answer choices, so it's not going to help us that much. We look over at the next one, and we see that 2 is only in 1 answer choice. So again, that's not that big of a help. So we want to go ahead and try to start with 3, since 3 is in both, is in 2 answer choices. That's our, remember, our normal Roman numeral technique. So look at the trend for 3. Surfactant water, weaker than water. So they're saying surfactant with water is going to be less than our water. So H2O interacting with H2O. Now, if we accept 3 to be true, okay, what they're saying here is that the interactions between the surfactant and water is less than the water-water interactions, right? Well, if you think about that, it makes sense. Water has lots of very high, strong hydrogen bonding. And if the surfactant-water interaction was stronger than the water-water interaction, that would be like dissolving a salt, right? Instead of a dipole-dipole interactions, we now have an ion-dipole interactions, and it's going to spread out in the actual solution. Well, we're trying to reduce the surface tension, the tension on the surface. So I want the surface-water interactions to be weaker than the water-water, so that the waters want to interact with one another more than they want to interact with the surfactant, so the surfactant stays on the top, because I'm trying to reduce their surface tension. So we get rid of answer choices C and A, because they do not include 3. Now if you notice, 2 cannot be included, so I get rid of that one right now, and now I consider, is 1 going to need to be included as well? So we go back in 1, surfactant to surfactant is less than surfactant water, okay? If you think about that, the surfactant-surfactant interactions, if they had a greater attraction than surfactant had for water, then it would act like a fat. Then it would act like a lipid. It would clump to itself because it has a stronger interaction between itself than it does for water. So we want to happen here is water-water still is a greater interaction. Surfactant water is going to be in between, and surfactant is the weakest force. And so that was going to allow us to do what we're trying to do here, which is reduce the surface tension. We're trying to reduce the tension or the attraction of water molecules at the surface there. And so our correct answer is going to be D on number 2. Okay? Questions on number 2? Questions there? All right, number 3 gives us a big list of different molecules to look at here. Okay? Now, one thing we do, of course, is go back and get into our actual passage and look and see what's going to be the biggest influence on the reduction of surface tension. Now, if you notice, of course, back in our figure 2, okay, and they also mention them, of course, in the artificial surfactants, the one they abbreviate as that, what was it, the C12E4? All right. So the C12E4, if you notice, that is a neutral molecule, right? It doesn't have any charge on it. And it has the greatest reduction of surface tension. But if you compare it to the other ones, you see that all the other ones are going to be Zwitter ions. So the others are Zwitter ions. Yes, they are overall neutral, but they still have a charge to them. And if you look at where they're ranking in that figure, they're definitely having a less of a reduction of surface tension, and it takes more of them to do it. So the trend we're going to want to look at here is for a neutral molecule, like C12E4. That was the one that had the greatest reduction in surface tension. So if you look at answer choice A, you notice, of course, that answer choice A, that's going to have a permanent positive charge. Well, that definitely is not going to be one, because we want it to either be at least neutral or at least in a Zwitter ion form. Now, if you notice the other 3, they give us your pKa's. And that becomes important because, remember, we're in the lungs where the pH is equal to 7.4. Then you look at the next one, B. You see that B is going to have an amine group, and its pKa is the 6.1. So in B, if the pKa is 6.1, and we're now at a pH of 7.4, what happens to that amine when we are at a pH above its pi point? Okay, oh, sorry, the pKa point. Will it deprotonate or not deprotonate? Okay? Well, it's going to deprotonate. Okay, so if it's going to deprotonate, the charge on this is going to deprotonate, and therefore the charge is going to be neutral. Right? There's no more charge on it. We lose that extra hydrogen from that amine group. So that's making B seem okay. All right, because we're seeing that deprotonation there, and it's a neutral molecule. Then we look down at C, and we see that C currently has a carboxylic acid at the end of it. But you see also that its pKa is 4.9. If we're at a pH of 7.4, is it going to remain protonated, or will it deprotonate? That's right, it's going to deprotonate, and because it's deprotonated, that's going to give us a negative charge. So C would have a negative charge at that pH of 7.4. And lastly, to extend it, if you look at D, again, we've got another amine group, but the pKa is given as 8.1. So this one will also deprotonate, but of course when it deprotonates, you're going to see a charge now. I'm sorry, it's not going to deprotonate, excuse me. It's going to remain protonated. All right, so remain, because we're at a pH below its pKa, so it remains protonated. Remains protonated, and therefore, of course, it's going to have a charge. That would be with the protonated, it would be a positive charge. Okay? Now, questions on number 3. Questions on number 3. All right, well then let's look at number 4, the last one here. And number 4 is asking us about the actual experiment describing the passage, which of the following is true regarding the surface enthalpy and entropy of water upon addition of surfactant. So we go back to that table here, and we see that when we have a decrease in entropy, all right, that's also an indication of a decrease in surface tension. So if you notice, of course, that both B and D saying that the entropy is going to increase. No, entropy is going to decrease, okay, as we add surfactant. Entropy is decreasing. So you can think about this one as kind of like a 2 by 2. All right, a 2 by 2. We got rid of 2 of the answer choices just because of the entropy factor. Now, that comes down to then the surface enthalpy. Is it becoming less negative or more negative? Well, what are we doing to the overall interactions and bonds there? The intermolecular, not bond, well, the intermolecular forces, right? We're trying to reduce the intermolecular forces of the water molecules by basically wanting to kind of have another pull on them, right? So the overall that we're seeing here, right? The weak interactions between the surfactant and the water are going to decrease the overall enthalpy of the surface molecules. So we're going to see, of course, a decrease in entropy. And lastly, as we were just saying, we're seeing an overall decrease in the interactions of those molecules. We're reducing that surface tension. So, of course, it becomes less negative. So the surface tension is less negative. So, of course, since it's less negative, it is in effect decreasing. It becomes less negative. Not decreasing, becomes less negative. And A is our correct answer. Questions on that passage? All right, great.